Hello everyone, this is Dr. Young, and in this video we're going to talk about solvents. We're going to talk a lot about the solvent effects and how they affect like the rates of SN2 versus SN1 reactions, but I want to take this opportunity to talk about solvents in like sort of the grander picture and how a chemist decides how they want to, or which solvent that they want to pick for their reaction if you're doing brand new chemistry. So solvent choice, right? It's a big topic, and first I have to mention, the green chemist in me has to mention that I'm saying solvent choice, but the best solvent is no solvent, right? So the best solvent, the greenest solvent, is no solvent at all. And I say best because I'm looking at it from the point of view of a green chemist, but because then you don't have to worry about the flammability of it, you don't have to worry about the toxicity of it, you don't have to worry about buying a solvent, you don't have to worry about paying to get rid of a solvent, you don't have to worry about solvent interactions. It can just be really, really convenient. The main disadvantage of not having a solvent is that it's harder to control temperatures and exotherms. So if you just have two reagents that you're grinding up together, sometimes it can get real hot and real dangerous real fast. So that's one disadvantage of not having solvents. But if you have to choose a solvent, there's just countless solvents that you can pick, right? I put up here a list of some: water, THF, acetone, ethylene glycol, toluene, benzene, acetic acid, HMPA. I mean, there's countless solvents out there that you can use. So if you're doing research, you're trying to come up with a brand new reaction or something like that, or you're just like, hey, I need to react with this with that, and you don't have some literature preparation, what we're looking for is a perfect solvent that will dissolve your reactants. It doesn't always have to dissolve your reactants, but it's usually best if it dissolves your reactants. We also need for it to not react with the reagents, right? If I'm adding a base, I don't want it to do an acid-base reaction with my solvent. I want it to do a base reaction with my substrate, with my reagent. So you want to make sure that it doesn't accidentally react with your reagents. You want it to be pretty inert. You also want to make sure that it's safe, right? That it's not going to blow up on you, that it's not so toxic that if you spill a little on your hand, you're going to die. You want to make sure that it also helps if the solvent speeds up the reaction, right? Because time is money. You don't want to be spending forever watching something stir for 4 days when you change solvents, and it could be done overnight or in a couple of hours. And lastly, you want to make sure that you can remove your product from your reaction mixture easily. You want to be able to remove your solvent from your product. And I'll talk about that a little bit more, but that means either that like your product crystallizes out, so it's really easy to just filter your product away from your reaction mixture, or it means that your solvent is relatively low boiling, so you can just evaporate it off. Those are kind of the main things that we're looking for a perfect solvent for a reaction. So if I take a closer look at these, one by one. First, we want to talk about like different types of solvents that are out there. And the three main camps that we go for in terms of their physical property are the non-polar solvents, the polar protic solvents, and the polar aprotic solvents. And the definitions aren't new. I mean, these are exactly the definitions you would expect, right? By non-polar, we just mean mostly C's and H's, right? Mostly C and H, just non-polar bonds. It's just going to be hydrophobic. By polar protic, it's got to be polar. And by protic, what we mean is that it can either hydrogen bond. Sorry, let me write this differently. If we're looking for polar things that are protic, what we're looking for is solvent molecules that can be hydrogen bond donors. Hydrogen bond donors. That means they have an H, right, attached to an O, an N, or an F, right? So just your normal hydrogen bond stuff that you learned from Gen Chem. So that's mostly our polar protic solvents, or things like acids. So I'll also put that, right, or acids. All acids would be considered protic solvents. Now, if I look at the polar aprotic solvents, that just means the things that cannot be hydrogen bond donors. I'll put cannot be H bond, hydrogen bond donors. Right, so they're polar, they still have dipoles and everything, but you can't like hydrogen bond. So if I look down at these, like, what, 7 examples that I've got down here, first, if I want to categorize these into these different groups here, I'll just look at them and ask myself, okay, well, do I have any partial charges, right? So for this first one, I have a partial charge because I've got an O attached to C. Same thing for this one. I'll just put these partial charges in here real quick for us. S minus, S plus, right? Water. We've seen 1,000 times, right? So far I've got a lot of things that are polar. Here I am at benzene. That's all CHs. Hexane's all CHs. And then DMSO over here. And just so we have names of things, right? This is THF, which is tetrahydrofuran. Tetrahydrofuran, right? And furan is this where you have the alkenes in there. So tetrahydro just means it's furan, but you've added 4 hydrogens. So you get that molecule. This is acetone. I'm guessing you know what water and ethanol are. Here's benzene. You know what hexane is. And this is DMSO, which stands for dimethyl sulfoxide. So DMSO. So of these 7, the only ones that I have that are nonpolar are benzene and hexane, right? So if I take a look at benzene and hexane, they're all CHs, and I don't have any dipoles on them, so they're nonpolar. So I'll put those as examples down here. So we have benzene, we have hexane, and there's lots of other nonpolar solvents. Toluene is really popular because it has a lot of properties of benzene, but it's not as toxic. It's not as carcinogenic. Sorry, toluene. It's not as carcinogenic as benzene is because it gets metabolized differently. Same thing with heptane. It is a slightly larger, so it has a lower vapor pressure, so you don't tend to inhale it as much, so it's less hazardous in that way. People use things like cyclohexane. There's all kinds of nonpolar solvents. What we're going to see for us for this section, we are going to avoid the nonpolar solvents because they're not going to dissolve our ionic stuff, right? We're doing ionic reactions right now, so they're not going to dissolve things very well. So we tend not to see the nonpolar solvents used very often. Now, between the polar protic and the polar aprotic, so I've taken care of benzene and hexane. Check. I've categorized those. And now I want to look for the ones that can be hydrogen bond donors, right? Do they have a partially positive hydrogen attached to an N, an O, or an F? And so if I look at THF here, I don't see any H's that are attached to an N or an O or an F. All the H's are attached to carbons. So THF is not a hydrogen bond donor. It's just a polar molecule. This would be a polar aprotic. And that's different than ethanol here, right? Ethanol does have an H attached to an O, so it can be a hydrogen bond donor, so it would be polar protic. So I'm going to put ethanol here for my polar protic. I'm going to put THF here for a polar aprotic. Because again, the big difference is, can you be a hydrogen bond donor or not? And so I've got those two done, THF, ethanol. Water is going to be the same thing, right? Water's like the hydrogen bond donor that you've probably seen 1,000 times. So I'll put water here too. And really any of the alcohols. It could be methanol, isopropanol, anything that has an OH dangling off of it is definitely going to be a polar protic. But that would also include things like acetic acid, right? Things like any of the acids, acetic acid, stuff like that would also count. Any amines solvents. So sometimes we do reactions in like liquid ammonia, for example. So that might be a polar protic solvent that you might see if you do some sort of amine solvent like ammonia, like NH3. And then if I take a look at acetone here, so my fourth one, acetone also has H's only on carbons, so that's nonpolar, so that is going to be aprotic. And then lastly, same thing with my DMSO on the right-hand side, right? The carbon right here only has hydrogens on it. The carbon right here has hydrogens on it, but those hydrogens are not on N or O or F, so they're not hydrogen bond donors. So I'm going to put acetone and DMSO in my polar aprotic. DMSO and acetone. And there's other solvents. There's HMPA. There's all kinds. I mean, we don't have to come up with a super exhaustive list, but basically, you know what nonpolar compounds are, so that's easy to spot. More or less the alcohols, things that have an H on an N or an O or an F, those are going to be polar protic, and then everything else is going to be polar aprotic. I always tell my students, I'm kind of joking, but not really, that if you see a solvent and you're not sure what it is, and it's an abbreviation like HMPA or DMSO or THF, and you're not really sure what that looks like, probably it's polar aprotic. It almost certainly is polar aprotic. It's not always true, but it's probably polar aprotic, like DMF, for example. I'm not going to tell you what DMF is, but you see it's an abbreviation. Maybe you don't know what it is. Assume it's polar aprotic, and it is polar aprotic. But again, I'm just trying to make a point here. Now, why do we care about this? So we said that when we pick our solvents, we need to make sure that they can dissolve the reactants here, right? And so here I have it's mostly nonpolar, relatively nonpolar. We do have a polar carbon-bromine bond, but mostly it's just C's and H's. So this is fairly nonpolar. It does have one polar bond on it. But most importantly here, we have an ionic compound, right? We have LDA. And so if I'm going to dissolve these reactants, right, these reagents, I need to pick a polar solvent. I need to pick something that has some polarity to it, because I cannot dissolve LDA, right, the lithium ion and the N-, I cannot dissolve that in hexane, for example. What's going to happen is if you add LDA to hexane, that salt is just going to sink to the bottom. It's not going to do anything. It's not going to react with your stuff, right? Try adding salt. It's like adding table salt. Like you can do this at home. You can add table salt to oil, right? Get out a bottle of oil, get out some salt, throw your ionic compound in your relatively nonpolar oil, and you're just going to see the salt sink to the bottom and sit there, right? It's not going to dissolve it. So for these SN1, SN2, E1, E2, we usually tend to go with a polar solvent. Whether it's polar protic or polar aprotic kind of depends, but we go with a polar solvent. So that's going to be one of your main considerations. Now we want for it to also not react with the reactants, right? I don't want my solvent to react with my reactant. So I need to look at something like in this example, I have LDA, which is a very strong base. And so what that means is that I need to avoid any alcohols. Avoid any alcohols or acids, right? Because if I take my LDA molecule, so I'm just going to redraw it over here so I have a little more space. If I have my LDA compound, and I add something like, say I'm going to try to do this in just ethanol. I'm just going to do this reaction in ethanol. I feel like it's going to be slick, right? Ethanol is relatively non-toxic, pretty safe. You can make it from bio feedstocks, everything. The problem is that my LDA is not going to act as a base to do my E2 reaction I want. What's going to happen is that it's going to be so basic that it's just going to deprotonate my ethanol. And then that's going to kill my base. Right? Then my base is going to have a hydrogen on it. It's not going to be negative anymore. And then I'm going to have ethoxide. Right? So I'm just going to do an acid-base reaction by accident. And you can't not do the acid-base reaction. Acid-base reactions are so fast. They're really, really fast. It's the quickest reaction that you're going to see. So they're going to outcompete things like E2s, for example. And you'll notice that, like in this particular case, I started with LDA, which is a nice big bulky base, which would give me the Hoffman product. But if I choose ethoxide, it might give me a Zaitsev product, because now I have a small, strong base, a weaker base, but still small and strong. So you want to really pay attention to what solvent you're adding and will it react with your stuff. Right now, for us, probably acid-base reactions are the only considerations you have to really worry about. You also want to ask yourself, is it safe, right? Not a lot of books talk about this, more and more are, but again, I have a green chemistry background, so I really care about this stuff, right? Is it safe? I want to know, how green is it? Right? Is it renewable? Can I make it from just like, for example, fermenting extra corn or something like that? Is it non-toxic? Is it explosive? If it gets out into a river, is it going to kill everything in the river? Is it going to give people cancer? All of those sorts of stuff, right? So when you're asking about how safe is it, we care about explosive hazards. Is it explosive? How flammable is it? Right? Is it going to form peroxides? How toxic is it? All those sorts of things, right? So you want to make sure that it's safe. One example I mentioned before is that you can compare benzene to toluene. Not that any of them are things you want to like eat or anything like that, but if you compare benzene to toluene, benzene is quite carcinogenic, not good. We try to avoid it. Toluene is very, very similar in that it's got this aromatic ring, so it has a lot of the same sort of properties and can pi stack and all these interesting things, but it has this extra methyl group on here which allows it to be metabolized by your body differently, and so it's much less toxic and much less carcinogenic. And so it's an easy switch, for example, to just pick the greener solvent. And there's lots of lists. Pharmaceutical companies put these out all the time. They're constantly looking at ways to make their factories safer, but also ways to save money. And often if you have a less toxic solvent, it is going to cost you less money because you don't have to pay a high waste fee for some really toxic solvent or really toxic waste that you have to get rid of. So you also want to pay attention to how green, how safe it is. Another example that I tell my students is when I was in grad school, someone was asking me to use HMPA for a reaction, which is hexamethyl phosphoramide. And I asked them where it was, and it wasn't on the shelf with all the other solvents. And I was kind of curious. It wasn't in the locker. And they're like, oh, right, it's in the hood. And it was in the back of their hood, behind all of the stuff for the glassware, the schlenk lines and everything, behind a post, hidden in the corner as close to the venting in the fume hood as they could get it. And I asked why, and they said, oh, yeah, no, it's like super toxic. And I looked it up, and it was very, 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 very toxic. And so I was like, well, is there something else we can use? Because I don't really want to like send myself to the hospital today or anything in case it spills. And it turns out that DMSO has very, very, very similar properties. I was looking for a really good hydrogen bond acceptor. Very, very, very similar properties, but it's like not toxic at all. Like DMSO is super non-toxic. So functionally, they're both polar aprotic solvents. They're both very polar, but one is very toxic and the other is not very toxic at all. So there's easy time to make considerations like how much damage you want to do to the environment and yourself. Is a question that you should be asking when you're doing chemistry. Does it allow for a fast reaction? So this is the part that is emphasized in this chapter of this book, and that's the difference between using a polar protic solvent and a polar aprotic solvent. So that's what I want to talk about next. So polar aprotic versus polar protic, right? In this reaction here, I have my primary halide, I have my my small strong base. That's a good nuke. So I know I'm doing an SN2 type reaction, right? I know that my hydroxide is going to come in here, do a backside attack, kick out the iodine, one concerted step. But I noticed that I didn't put a solvent there. So I get to pick what solvent I want to use here. And what solvent I pick is going to have a large effect on how this nucleophile can add, right? So I'll do DMSO, which is, again, dimethyl sulfoxide. And I'm going to draw out all of the atoms here just so we can kind of see them better. And I'm going to also pick ethanol. And if I take a look at these, right, I'm going to go ahead and put on my partial charges if I have any. I've got a negative, whoops. I've got a negative on that O. I've got a positive on the S, right, because oxygen's more electronegative than sulfur. And then same thing here, I've got a negative on that O. And I've got a positive on that carbon and a positive on that hydrogen, right? So they're definitely both polar, right? This DMSO is polar, but it's aprotic because it doesn't have any H's on nitrogen, fluorine, or oxygen. And versus ethanol is polar, and it is protic, right? Because we have this hydrogen right here is on an O, right? There's your hydrogen bond donor. And the reason this is important, what I'm going to do is I'm going to kind of represent the hydroxide as just like a circle for now, just to make my life a little bit easier. I'll draw that over here on the right-hand side. let's just say that this sucker is the hydroxide, the O-, right? It's an anion, it's an O-. And since it's an anion, right, it's negative, if I put this in these solvents, right, I just bathe it in the solvent molecules are going to align themselves so they can interact with this ion. And since it's an anion, that means the positive parts are going to be attracted to the anion, right? I'm going to have this positive part be attracted. And so what you see here is that, like, I'm going to do the DMSO first here. I've got my hydroxide, and I'm going to try to get it as close to the positive charge as I can, right? Here's my negative. I'm trying to get it as close to this positive charge as I can. I can get about this close because I'm going to start bumping into these hydrogens on either side, right? And so I'm going to have this attractive force here. I'm going to have this ion dipole force. Right, this is an ion dipole attraction. And I'm going to try to get it as close as possible to that positive sulfur, right? The negative hydroxide is going to try to get close to the positive sulfur. And I can do the same thing with the ethanol, only what's different about the ethanol is that the positive part, the H, is just sticking out and it's not really being blocked by anything. It's not being sort of shielded by these other H's. So I'm able to get my hydroxide right up to it. Right, so I'm able to get that partially positive I'm able to get that partially positive hydrogen right next to my anion. So I have that ion dipole attractive force. Now, what you should notice is that, or what you should remember from Gen Chem is that how close you can get, right? The closer you can get, the tighter the interaction, the stronger the interaction. The further apart two charges are, the lower the interaction, the weaker the interaction is going to be. So if I look at my DMSO example, right, these are further apart. And so this is a weaker interaction. Here they're closer, which means it has a stronger interaction, a stronger attraction. Right? And it's just largely a proximity thing, right? It has to do with the charges, the size of the charges, but also the proximity. How close can you get? And this is generally true for any polar aprotic solvent. For the aprotic solvents, they do have partial charges, partial positives, but they're going to be kind of shielded and kind of like blocked by just regular CHs. And with the protic solvents are always, by definition, going to have a partially positive hydrogen that's just sticking out from the molecule somewhere that's relatively easy to interact with, to have that ion dipole attractive force with. So why do we care about this? I drew these. It's kind of the same thing that I had before, right? I have the DMSO, I have the ethanol, left versus right. Same idea, but only I drew more of the molecules, right? And I drew 4, right? I have 4 right here around the hydroxide, 4 DMSOs. Realistically, it's probably more. Same thing for the ethanol. I only drew, 6 ethanols? Realistically, it's probably more. But the point is that they form this solvation sphere, right? This is your solvation sphere. Where the solvation sphere is just when an ion is in a solution, right, is in some sort of solvent, that solvent just binds to it and just surrounds it, right? And by binds to it, I mean there's just those attractive forces that keep the solvent particles close to your dissolved ion. And that's the same thing for both of these, right? These are both solvation spheres. Now, like I said in that previous slide, one of these solvation spheres is weaker and one of them is stronger, right? And if you remember what I said in the other slide, in the previous slide here, the protic bonds, those were the stronger ones, right? That's where they're closer together, and so this is a stronger solvation sphere. The solvation sphere with the DMSO, with the aprotic solvents, is weaker because the charges are not as close together. And what's important about that is that means that it's easier for my nucleophile base to go do something if there's a weaker solvation sphere around it. If it's able to get rid of those solvent molecules so that it can get to the electrophile that it's supposed to do, this is supposed to attack, like an SN2 or something like that, I need to be able to move one of these solvent molecules, right? If this hydroxide is going to go attack something, let me draw this, right? If I forget what molecule I had, something with an iodine. But the point is, if I want my hydroxide to be able to do a backside attack, what has to happen is I need to move solvent molecules out of the way. And if it's a weaker solvation sphere, it's going to be easier to move the solvent molecules out of the way. If it's a tighter solvation sphere, a stronger solvation sphere, it's harder to move the solvent molecules away, and therefore it's a slower reaction. So what we tend to see is that these Aprotic, right, here's the Aprotic tends to make SN2 reactions and E2 reactions faster. And that's because they allow what a lot of books call a naked nucleophile. And what they mean by naked nucleophile or naked base is they mean that it's not covered by the solvent particles as well. It's not covered by the solvent molecules as well. It's free to just go and act as a base. It's freer to go and act as a nucleophile. And that's opposite from these, right, from the polar protic solvents. For these, SN2 and E2 are slower. And that's because the nucleophile or base is hidden by the solvent, is more hidden by the solvent. Is more hidden by the solvent. And I'm saying it's slower. I'm not saying it prevents it. We can definitely do SN2 and E2 reactions in a protic solvent. That's not the issue. It's just that it might go a little bit slower. That's all. It's not going to change your reaction type. It's not going to be like, oh, all of a sudden now we're going to go SN1 instead of SN2. Nothing like that. It's just a little bit faster or a little bit slower depending on what solvent you pick. So if you wanted to have a faster SN2 or a faster E2, you pick an aprotic solvent so that nucleophile is more naked. That solvent molecule is not as tightly bound to your nucleophile. Now, here, right, I have the first step of an SN1 reaction, right? Leaving group just leaves. I'm just talking about the leaving group just leaving here, right? In both of these, they're just SN1s. But all I want to point out in this one, it's kind of the same idea. I just want to point out that, again, if you have an aprotic solvent, like with the DMSO, right? This was aprotic again, versus protic. These are the same solvent molecules I used before. If you have an aprotic solvent, again, the distance between your partially positive sulfur and your partially negative leaving group, whatever it is, bromine, chlorine, iodine, whatever it happens to be, is going to be longer than if it's protic, right? If it's protic, it's going to be a lot closer together. So you have a stronger attraction there. And then once that bromine pops off, right, and we get our carbocation intermediate, our tertiary carbocation here and here, now we're talking about the interaction between that leaving group that just left, the bromide, chloride, iodide, whatever, and the solvent. And again, you can see it's the same thing, that the polar protic has a tighter interaction, is better at stabilizing the ion than the aprotic one is. So what we tend to see with these is that protic solvents stabilize the leaving group and the resulting ions better than aprotic solvents. And it's the same idea. It's just that they can get closer to those negatives or partial negatives, right? If you're protic, you have a partially positive hydrogen that can get closer, stronger interaction, stronger attractive force, and so it's a little bit faster. So we actually see the protic solvents are a little bit better for SN1 and E1 because a leaving group has to leave by itself and you get these ions. So to summarize that again, right? So faster reaction, we want protic solvents are going to give you faster SN1s or E1s because they stabilize those carbocations. Aprotic tend to give you faster SN2s or E2s because they give you that a weaker solvation sphere around your nucleophile or base, right? The aprotics tend to have that weaker solvation sphere. Protics tend to have a tighter, stronger one. So if you had to pick, and we'll do an example here in a second, if you had to pick, if you're doing an SN2 reaction, go with an aprotic solvent. If you want to do an SN1 reaction, you're going to want a protic solvent. And then lastly, like I said, being easy to remove. I kind of mentioned this already before, right? Ideally, you want you want to have something that has a low boiling point, right? So you can evaporate it so that it's easy to evaporate away. Much easier to evaporate something with a boiling point of 80 degrees as opposed to something that has a boiling point of 200 degrees. You would spend a huge amount of time and energy trying to heat and use a vacuum on that thing to get it off. So usually lower points are just easier for just physical property reasons. And then, like I said, another example would be ideally, you'd want your product to not be soluble. Not soluble in the solvent. That would be great too. I did this one reaction just to give you kind of an example of what I'm talking about here. I did one reaction here where I was basically trying to, I'll just use this as an example. It's something like this, where I took triphenylphosphine, so PH3P, and I added it to an alkyl halide. And what happens is they just do an SN2 reaction, but the phosphorus stays on and it keeps all of those phenols. And you make this compound. And what I did was I did it in, I think it was toluene. And when you look at this, this molecule, this bromopropane thing was soluble in toluene. The triphenylphosphine was soluble in toluene, but this was not soluble. The product was not soluble in toluene. So it just made a nice white powder when it was done. It was just a white powder that started to form. And I was just able to easily just filter that away. It was super, super easy to collect my product. Just filtered it with the Buchner funnel, done. There's no problem. So you also want to pay attention to like, how are you going to get your product back out? That's always an issue too. So those are the big things you want to consider. Again, I gave you kind of more information than you probably need. If you're going to go into chemistry or you're doing research yourself, then you should be thinking about all of these things. The main thing for this chapter is that difference between protic and aprotic solvents and SN2, SN1, and E2 and E1 reactions, right? So if you saw a question like, will a reaction between T-butyl chloride and water occur more quickly in a 90-10 water acetone mixture or a 50-50 water acetone mixture? So this should have a slash, right? Which one will it be faster in, and then explain yourself. So what you'd want to do is first figure out, are you talking about an SN2 or SN1 reaction, right? And so T-butyl chloride, I know that that's tertiary, right? T-butyl chloride's a tertiary substrate. And then water, I know, is a pore nuke. So that means this must be an SN1 reaction, right? So this is an SN1 reaction, which means I want a protic solvent. And I want a protic solvent because it's going to help stabilize the leaving group leaving. Right, and lower the activation energy. Now, if this is on a test for me or something like that, I'd want you to use complete sentences, but that would be, I would want all of those pieces in there, right? So that's what you'd want. So that means that in this then, so which solution, that means we want the most protic one, right? If I want it to be protic, I need to have the more protic solvent, which in this case would be the 90-10, right? Because water's the protic solvent, acetone's an aprotic solvent. So you'd expect this reaction to go faster if there was a higher percentage of water in there as opposed to acetone. So I'd pick that. I'd pick 90-10 water acetone. Why? Because it has more protic solvent in it, and that's going to help stabilize the leaving group, which lowers activation energy. Then for the second question, in which solvent will a reaction between 1 chlorohexane, 1, 2, 3, 4, 5, 6 chloro, so 1 chloro, and sodium methoxide, which is just written out there. occur the quickest. So again, I'm going to kind of analyze what I got going on here. I see I have a primary halide. I see I have a good nuke that's a strong base. So I'm thinking that this is an SN2 reaction, which means I want an aprotic solvent. That's going to be the fastest one. I want an aprotic solvent. And if I look over at my choices here, water's protic because it can hydrogen bond. Ethanol's protic. It's also a hydrogen bond donor. Hexane's nonpolar, so that's probably going to be problematic for these reagents, right? I can't dissolve sodium methoxide in hexane. And THF, though, is polar aprotic. Ding, ding, ding. So that's going to be the best one. That's the one I want. I want the THF. And again, if you don't remember what THF looks like, if it's an acronym, it's probably aprotic, but THF, again, was the 5-membered ring with an oxygen as one of the members. So I hope that you have a little better sense of how solvents are important for these, how to decide on solvents if you're just kind of wondering like what solvent should I use or not use. Do lots and lots of practice. Happy studying.